This information is brought to you by Charles Sturt University.
Welcome guys, thanks for being patient while I get myself organised. So what we've been looking at so far is looking at sets. And so sets and logic, which we'll also touch on today, are examples of Boolean algebra. And so the things you sort of do with sets and logic's really important for computers, really helps. It's the same sort of thing actually. It's a very similar approach to both of them, and those sort of skills are really important when it comes to trying to simplify logical expressions, etc. But also give a sense of trying to work out when to prove things are correct or not. So really important the idea of proofs. And so looking at some of these for that particular reason. So what we were looking at last time was looking at the different operations for sets and how can you simplify those sort of expressions. When you've got lots of intersections and unions of sets, how can you simplify them? What sort of rules are there, etc. And so a useful way in practice to deal with many of these things is to use Venn diagrams, which is just a nice visual representation of what sets are and helps you prove and simplify things, etc. if you need to. So just want to one for the moment, just sort of show what you can do with Venn diagrams. So this is the result. So pretty much that A intersection, so, and the cap symbol means intersection. You can often just read the word AND. So B and C is the same as saying A and B and C. So I'll give you a reason, give you some names what this result talks about. This tells you that intersection, or AND here, is associative, which is a very fancy way of saying if you've got lots of ANDs in a row, you can do them in any order you feel like it. You can do the first two, or the last two, it doesn't matter. So in terms of things that you know, addition and multiplication are associative. So you can do them in any order you want to at all. Division is not. So if you had 1 divided by 2 divided by 3, if you had to do 1 divided by 2 first, it gives a different answer if you do 2 divided by 3 first, it gives you different answers. That's not associative. So you're familiar with things that are both associative and not, and whether you realise it or not. While the logic operators, all the set ones are associative, which is really nice, which is really good for simplifying it down. So let's try to prove that it's actually right. And that's a property, but let's actually prove it's right. So the way to do it is to use pictures, I think, Venn diagrams. So what I'll do is I'll draw a picture for both sides. There's two sides of the equation. So we'll call the first picture the left-hand side. And what I want to do is I want to try to draw a picture corresponding to that expression. So I've got A, B's and C's. So I have to put a picture down for A, B and C. And like I mentioned the other day, I would like to try to prove this result in full generality. So I need to make sure the picture covers all possible circumstances that you could ever encounter. All possible overlaps need to be included. And the way to do that is just to draw that triangle-shaped picture. So A, B and C. Which that's all it means. And so now I would like to try to colour in what the left-hand side corresponds to. And I'll do the same thing for the right-hand side. That's what I'm going to do. Now, basically do it one step at a time. Now, if it really necessary, you could draw more than one picture for the left-hand side. That's actually okay to do. Depends. We'll see how we go. So the way to do it is to start with the simplest things first. The normally way I think about it is doing it from the inside out. So you've got a compound expression. Let's go for the inside. That looks the simplest bit. So the simplest bit is B and C, essentially. So I want to colour that part in first. So the B and C is what part? So the AND bit, as you're trying to say, is going to be the overlap between sets B and C. So that part down the bottom, it's green. That's B and C. And now what I want to do is I want to do A and that. So I want to know the overlap essentially in terms of the picture. I want to know the overlap of A and the green part I've coloured in. So you just got to go, well, what part of that green part overlaps with A? The middle part. So this part here is the overlap of A and the green part, essentially. Now, you need to make sure that if you have to do this for an assignment, and the answer is you do, so there's a question that you have to do this for an assignment, it's not this particular question, I might add, but something similar to it, you're going to have to put diagrams in so the marker can tell what you're thinking. So sometimes that might require using two pictures, or it might require what I'm trying to do at the bottom here is just labelling it. So I've used different colours, I've just tried to show them in differently. So I've got different colours, it's all black and white, different shading. In practice, you guys will probably find it easier to get a piece of paper and write it out by hand. And if you're going to do that, you're probably going to scan it in to submit it. The scanner may or may not have colour. Depends what you've got, I guess. If you're going to scan it in black and white, colour won't work so well for you. And you're going to have to think, well, it's going to put, diagonal lines going one way versus diagonal lines the other way to separate the two regions out. So just, switch your brain on in gear, put your brain in gear when you do it and you'll be fine. But just got to make sure people can understand what you're doing. Sometimes it requires a little few words here and there. It doesn't go astray. The markers just have to understand it. I guess that's the real key part of it. My benefit today is I can speak words to you. You can't quite do that inside me. So that's the left-hand side. And you can say it's the left-hand side corresponds to the little blue region I've coloured in the middle. So I want to show that the right-hand side corresponds to the same little bit being coloured in, and that hence proves it. So I draw my three overlapping sets again. So my A, B and C, and then do the same sort of process. So again, work from the inside out. So the inside, in this case, is the A and B. And again, just think that cap being characters intersection. I think best thought of as just being and. So A and B. So what's the overlap of A and B in this case?
Yeah. Left-hand bit.
It's hard to describe it.
Left-hand ellipsis?
Yes.
So, something like that, yep. Sounds good. So it's not a circle, it's the ovally sort of shape.
American football.
American football, yep. So that's the A and B, the overlap between those two. And then we want to know the overlap of those, that one, and C. So what's the overlap between that green part I've coloured in and C?
The middle again.
And it's again the middle, which is good because that's what we're hoping it to be.
It's the same. Half an American.
So the whole green part is the A and B. And the blue part we've coloured in is A and B and C. Can everyone see I've got those pictures? Now we just need to put a little sentence down the bottom to say we've finished, essentially. Since both diagrams are the same, so we've coloured in the same part, the left-hand side equals the right-hand side. Hence the result, effectively.
So it's only the blue part on both diagrams that matters?
Yes. So you need to label it sufficiently clearly enough that that's what you're comparing. So maybe you need to say, so since the blue parts of both diagrams are the same, that's what shows the left-hand side and the right-hand side. Yeah, thanks for that clarification. And you can prove this you can use this same technique for lots of stuff. Now, the diagrams work well when you've got 2 or 1, 2 or 3 sets. When you get to about 4 sets, it gets pretty messy to draw, and you have to work out something else. But lots of the key results we want to deal with just tend to deal with 3 sets at most anyhow, so we're fortunate. That's okay. that's my other pictures. So you can get computer generated if you want to go fancy enough. I reckon for your assignments, just drawing it by hand would be much quicker. And I don't want you to waste time learning how to do that stuff when just doing pictures is more than satisfactory. You can use paint.
That's genius.
You wouldn't use a scanner anyway, would you? You'd take a photo with your phone.
Oh, sorry. A scanner probably means getting the right app on your phone. So when you can photo it at an angle, it does the projected correction for you. And
Buy the $17 in-app purchase to get colour ones, which is
Holy shit.
just do black and white. It's fine.
There is free album scanners you can get.
Yeah. So
Yeah.
something you use paint. I don't have Photoshop.
Use paint.
Google Drive and paint.
I don't care how you do it. My suggestion is for most people, paint's slower than doing it by hand and scanning it in.
3D model.
But I don't care. It's up to you. You're the one doing it. You need to make it clear. So you can do lots of things. So you can show using Venn diagrams things aren't equal. You can choose subsets as well. You don't just have to prove things are equal. You can do lots of different stuff with it. So let's just do this one last one. I've got more examples, but I'll only do one of them.
That noise is really like
They want to show that something's happening, I guess. That's the idea, isn't it? Okay, so I've got two sides here, left-hand side, right-hand side. I want to show you that they're not equal in this case. So basically the strategy for this is I'm going to draw a left Venn diagram for both sides, but I want to show they're not the same picture in general. So there's probably some circumstances when they are equal, but in general they won't be. And that's basically the strategy. Two pictures, not the same. So left-hand side, right-hand side. So left-hand side, I've got my three overlapping circles again, like that. So let's see what I can colour in. So again, work from the inside out. This one here has got the A union B, and again that cup symbol is a U for union, and it's just best thought of as being or. Just means chuck the two together. So a big part of the problem is just the overcoming the language, the symbols here. The cap symbol, what's the next one over there? That upside down U. And, yep. And we've got, that's the or again, and it's the and again. So this is saying, like, it's tempting just to swap the and and or around, and the answer is you can't do it glibly like that. I'll show what the correct result in a second. But so that's, so we've got to be careful. So the inside bit never least is A or B. Visually, what does that mean? So if I've got my green pen, colour in A or B, what am I going to colour in? So I'm going to colour in both circles together. That's the that's A or B. And when you're writing it to yourself, you can use or and. You can just use the words. You don't have to use the cup symbol. I don't really mind, but you need to be able to read the other one. Okay, so that's the A or B. And then we want to do this other bit. We want to do that and C, intersection C. So what does that mean visually? Sorry?
The right and middle American footballs.
Yeah, so it means take the overlap. So what part of that?
Yeah, he understands it that way.
No, I did. Oh no, I'm a pedant here. Ellipses have round edges, which is why I didn't like them before.
Damn.
sweet potato.
An eye.
It looks, I don't know what it looks like a really fat boomerang.
Okay, you can be creative describing it. So it's just the overlap between the green area and the blue part. So that's the A or B and C. So that's the sort of bit we've coloured in. So we've got on the left-hand side. So I want to do the same thing for the right-hand side. So I've got my 3 ones again, A, B, C. And again, let's go from the inside out. So the inside in this case is the B and C. What does that look like? Yep, so it's the, what have we gone for? The American football. The B and C in the bottom. So that's the overlap between the 2 bottom circles. So and just means overlap. Union means colour both in, everything in together. So to that end, the A or and this green region I've coloured in means colour both of them in together. So it means colouring in both all this red part at the top and colouring in the green part. So colouring in both parts together. Now, in order to show that visually, it might be easier just to only colour in the A part. My little legend here, I've got the red and the green together is the A or B and C. So any bits I've coloured in at all correspond to the union. So just to make sure you can see what I'm talking about, that sort of shape together, which is a circle little thing at the end of it, and maybe don't try to describe what it looks like in case you say something rude or something like that.
It looks like
3 grapes in a bowl.
no,
I don't know which one we're actually talking about.
An upside down apple.
a deflated American football.
Looks
like a bird, sort of.
So
Bit into it now. This is severe interpretation. Pikachu.
Wait, what?
Okay, fine.
It's like a sunset.
and the green part coloured in. So if you want to say that, it's A and the green part coloured in. Yeah.
It's like a psychoanalysis. Like, what do you see in this picture? It's like
Okay.
American football.
You mean like the Rorschach test?
Okay. So what's our conclusion going to be? So we've done the pictures for both left hand side and right hand side. Are the pictures coloured in the same way?
Hell no. Sorry.
And so the answer is no.
I know that's not.
And so because the answer is no, that means that proves they're not equal. So since they're coloured in a different way. And again, it might be helpful if you wanted to really communicate that, to reproduce the pictures slightly better than what I just did there.
Definitely not the dodgiest thing I've ever seen.
So if you
Speak up.
Yeah.
reproduce them 2 pictures, they're the 2 things we've coloured in to make it clear, and you go diagrams, that's the blue parts again, are different, and so the left hand side is not the same as the right hand side. And so you can use Venn diagrams to do lots of sorts of things like this. And I think it's a really useful skill to utilise because it so relies on visual things so much. It's much easier to handle than some of the algebra, which is what we're going to do next. So that's that part. Just as an aside, if you had A or B and C, what it really simplifies down to, so it's the correct result rather than an equals case, is actually you can think of and or intersection and union sort of just being a bit like multiplication. And so with multiplication you can expand brackets when you've got multiplication. Same sort of thing applies here. So you can really think of it as and B multiplication. So it's really like A times by C plus B times by C. It's sort of how you expand brackets. Same sort of thing applies here. And you've got to put some brackets around to make it legit. That's basically what the idea is. It's like
math.
It is.
In like a discrete kind of way.
Definitely is. So it's called expanding brackets colloquially. The fancy way of describing that is that it's called a distributive property. Now, why I mention these big words, you'll see in a second. But so that's one. So there's lots of properties which you could prove using Venn diagrams. But at the end of the day, I don't want to have to do a Venn diagram for every single step all the time. I'm just be able to pull out these things whenever I need them. So it's going to be useful in a second to have all these properties listed, and I'll show them to you. And you don't feel you have to write them all down yet. I'll show you where you can get them. Just print them off so they're all in one place, even. I'll come back to that. So you can do lots of other stuff. I've got a few others here, which I'm not going to do. So, as I said, what I'm leaning towards is I want to be able to say a bunch of properties that we can describe a set. So a bunch of rules that always apply. Now, the rules for arithmetic, so sums, multiplication, division, etc., you know them all just because you've grown up with that sort of stuff from little kids. And you don't know, there are lots of rules, you just know them. So you know that if you're going that 2 plus 3 and 3 plus 2 are the same. Like you know that. But you also know that 2 minus 3 and 3 minus 2 are different. There are lots of rules you just know automatically. There are similar rules that apply for these set stuff. Fortunately, most of them are pretty straightforward. Now, I'll show them to you. This is there on the screen. But I think a good way is just to help you handle them later. It lets me. Is in your exam, you're going to have to utilise these things for some question. And again, that's true for the assignments too. And so you are allowed a double-sided A4 sheet of paper in your exam. So call it a formula sheet, cheat sheet, same thing really. I've put an example one of those on the Interact 2 side. If you go to Interact 2, click on Assessment Items, about halfway down it says Formula Sheet, Example Formula Sheet. This is what it is here. You can see it. If you can read it from there, you're doing fantastically. But that's what it is.
The resolution of the screen is
this second page, which I'll zoom in so you can actually get a chance of seeing it.
I like it.
So the second page, among other things, lists all the rules that I expect you to know, and you can see what know means, just better look it up quickly. So all these different rules that you can utilise to try to prove various stuff. So I don't want you to have to memorise them. So they are there. It's good to understand what they're about, in grand scheme of things. Most of them are fairly straightforward, believe it or not. The ones that are, some are a bit, I'll mention, the one that's I think the hardest to remember is De Morgan's law, which is the one that's got a name essentially. So they're all of them listed here. So what you could do is, I recommend that as you're going through the subject, you plan what your formula sheet's going to look like. Now this is an example. You may hate it, that's fine, I don't care. It's up to you. This just shows you some things you can put in. But it does have these ones already. So in other subjects where I have these, what people do in practice is they print it out, get some scissors, cut out what they like. Well, you can do it electronically too. And then build your own one up from it. But add things as you need to. If I zoom right out again, you can see I've left a lot of white space there still. So even if you're just going to print it out and handwrite stuff around the side, that would work as well.
It's a not gate.
Yes, that's right. There's some logic there too.
It's very late today.
Please, so I encourage you for your first assignment, it's nice to have those list of rules there, for the first assignment for that matter. So you could utilise it already if you wanted to. The list of rules are in several places, but that's all in one go at least. So just as an encouragement to do that, it hopefully will help you, that sort of stuff. So let's just talk about what the rules are in my normal typeface here. So the first one's called commutative. Commutative just means the order doesn't matter. So you can just write the order A and B or B and A, same thing. So that probably makes sense. Move on. Next one is the associative. If you've got lots of ands together or lots of ors together, the order doesn't matter. Again, that seems believable. And we proved one of them just using Venn diagrams a second ago. So, but it seems, yeah, okay, I get that. I wouldn't have to think too hard about remembering that one. But it's useful to have the names. When you have to prove stuff, you can just be able to quote the name. That's probably the main thing I reckon you'll get for some of it in terms of the cheat sheet. Next one is that idea of expanding brackets or distributive. That really just means just treat them like expanding multiplication over a bracket. So this first one here is how do you expand a and something or other? You just do a and of each part separately. And you've got a or of lots of things, do a or of each part separately. Just like expanding brackets. Now, it's hidden by the new symbols, but that's what it really is about. You've got a bunch of key properties of, what's phi again? Remind me. The empty set. And what's U again?
Oh, look, nothing.
It's the universal set, which is everything. So this one's saying, if you've got A and A or nothing, what do you have?
You just have A.
Just A again. If you have A and everything, just A. So that's what. And again, you don't have to really, if you think what the symbols mean, of course they're right, hopefully. You've got complements, one. So if you say A and not A, well, they can't happen at the same time. It's an empty set. A or not A, well, either one or the other has got to happen. So that's everything. So use the universal set. They're called complements. Next one's idempotent. Idempotent means if you do it, it just gets the same thing again. So A and A is A, and A or A is A. And the De Morgan one. So I think this is the one that's hardest to remember. The one that's perhaps least believable. So De Morgan's law, have you seen this in 161? So pretty much, no, maybe not. Maybe it won't be hard to remember because you remember it from previous subjects. But basically, what it means is if you've got the not of an intersection, or not of an and, or not of an or, it just tells you how to rewrite it in terms of the way around. It's a useful way of doing the opposites of ands and ors, essentially what it's useful for. Now here it's phrased in terms of intersection and union, but you do the same sort of thing in logic. You've got special properties again. These ones, if you just read what it says, it goes, oh, of course it's obvious. That is A and the empty set. So if you've got A and nothing, well, you have nothing. And if you've got A or everything, that's everything. And when or, if you keep remembering, means inclusive or, so it means one or the other or both. So as soon as you do or with everything, well, that means everything's involved. And the last one's just if you do not a double knots, two negatives make a positive.
Because if it's nothing, then A can't be.
Okay. So they're the basic properties. And hopefully, if you do, the hardest thing is the symbols get in the way, I think. But if you understand what it's saying, you go, most of them are clear truths. The ones that are probably hardest are, I think, De Morgan's, which may not be for you, and the distributive laws, just because the symbols really do get in the way. So they're the ones you have to force yourself to try to engage with a bit more. And I said, you don't have to remember them off the top of your head, you have to look them up. That's what I'm heading towards. So now we've got all these, let's just try to do something with them. Okay. So let's try to use these sort of rules to prove something. So here we've got two an inequality with sets. We're going to try to use these sort of rules to simplify this expression. So let's just read it out loud. So you've got A or the empty set and A A or B is equal to A. If you want to try to prove these things, so sometimes in the exams and assignments, I just say prove it. And when I say prove it, you can choose whatever method you want to at all. Which means you go, I hate algebra properties and stuff, I'll just use Venn diagrams. Fine. Sometimes I'll say quite explicitly, using the rules of set theory or whatever it might be, prove these things, and then you have to do it that way. Even when it's written down that way, it doesn't stop you from trying to pull out some Venn diagrams to try to help you understand what it's about though. There's nothing wrong with that. Certainly an assignment when you've got more time, feel free to do that. In the exam, you've got less time up your sleeve, and so maybe you want to just go, I've got to do it directly because I'll run out of time otherwise. But assignment, take some time to understand it in different ways. That's okay. I'll draw a picture afterwards, but let's just try to do the algebraic fashion. So we'll start with either the left-hand side, and we'll do a bunch of steps using each of the properties one at a time so we get to the other side. So you need to start with the left or the right. Which one would you start?
Left.
Okay. So I reckon left-hand side's a good place to start. Why do you pick that?
Because it's got the phi in there.
Okay. It's the more complicated looking one. So going from complicated, making it simpler, tends to be easier than starting with simple and trying to make it complicated. I don't know. That's my personal preference. It's hard to know how to make it complicated sometimes.
I believe it's just because of the way you read it from left to right and stuff on the left-hand side.
Oh, no. Oh, because we're English speakers, left to right's more natural for us as well. But even so, if you write it another way, I still would start the complicated side first. So the left-hand side is this one here. So what I want to do is I want to try to simplify it, eventually to get down to A. That's what I'm heading towards. What's the thing that comes to your mind to simplify it first? Okay, so you can see there's an A union in both those two terms. So factorising that out is a good idea. So you can see I'm just factorising it out. It's a good way of thinking about it. In terms of those rules that we wrote down, the name for that, the one that deals with expanding and factorising brackets, is called the distributive law. And if you go, in reality, you're going to go, I'm not going to remember that name. So that's when you go to this formula sheet. Maybe not that big. And you go, okay, this is the rule which helps me to factorise or expand an A around brackets. That's the one I just used. That's the rule I just used then. So then I just go, and the name here listed is distributive, so I just put that in brackets. That's the rule I've actually used. So I've just factorised it out. What do you do next?
Nothing in B.
Okay.
You got everything basically.
Nothing.
So nothing and or anything else has always nice rules to simplify it down. So that's always good to go for. So let's read it out loud. It's nothing and B. So what is that going to simplify down to?
B is there, then nothing can't be there, so it's always going to be nothing.
Going to be nothing. And again, you just look up what the rule is. So it's this one here. So it's really just a property of the empty set. So it's a property of what it just really means. It's just all about what the empty set means. So the name is that's the special property of phi. Just about simply around what the empty set that symbol corresponds to, i.e. nothingness. Let's just write the same thing without brackets. I haven't really done anything here, just got rid of the brackets. So I haven't changed anything just yet. There's no rule required. So I now want to tell us something like this. A or the empty set. And it becomes A. And again, you go, well, rules that one. So you keep finding, you go, scroll along, and you go, there it is. A or phi equals A. And that's just an identity, called an identity. In terms of maths, it's really like just saying A plus 0 equals A, like 1. That's what it corresponds to. It's a bit like it's just like 1 plus 0 equals 1. So the union, the empty set, really just something like plus 0. It's the same sort of concept, mathematical concept. And so what you can see we've done is that A there is the right-hand side. So we've shown that the left-hand side is equal to the right-hand side by a bunch of steps, and we've clearly identified what each step is by giving the rule for it corresponds to it. Now, it worked out really nicely in that case. It may not always work so nicely like that because you can go in the wrong direction if you're not careful. and that is possible. So you just got a trial and error occasionally what's happening. So you might go something else. I'm going the wrong way. Let's try to do something else. Visually, what this rule states, that the left-hand side, the A, or the empty set really can be thought of as A. So just it's A and A or B equals A. That's probably a more logical way of writing it down. That's the result. So in terms of a visual approach, I've got two circles. The union is both together. That's just the A union B coloured in. And I want to work out. And I want to see what part of that overlaps with A.
He's got half nibbles.
So a monocle, I don't know what I'm picking up from the banner there. So if you can see, if we do the union and back the A again, you're going, well, the fact you've included B temporarily just all disappears. You can see that what we've already done is just colouring in just the A by itself. This is called the absorption property, or an absorption property, there's two of them when it comes to set theory. And so when you're doing both together, the A, all of it just being absorbed into the A is sort of the idea. The dual of it makes, the name comes more from the others, what's called the dual of it. So this is a common property you see. It's not it's not a simple one, but it's a common one you see. Which is why it's good on to prove it. It's just the next sort of tier along. Okay, so putting it simply, if you had to prove that two sets are equal or not equal, or subset of one another, etc., like that, if I don't tell you anything, you can choose whatever method you wanted to do with it. Which means you can pick the one you're more comfortable with, which could easily be Venn diagrams. I think for three sets they work really nicely. You don't have to remember the names, rules, or anything like that. You just have to remember that intersections overlap, or is colour both in, and not means do the opposite. That's about it. So the rules are fairly straightforward. When it comes to algebra properties, you have to remember a bit more, or be able to look them up. But these rules are really handy because at the end of the day, what we'll do these sort of things for is we want to have a complicated logic expression, which is what computers are about in the heart of it. How can you simplify them? How can you get the most simplified expression? So if I gave you just the left-hand side in this case here, how could you work out in a systematic approach what the most simple version of it can be? In this case, the answer is A, which is pretty simple, but sometimes it isn't always clear what the most simple thing is. So we'll work later on how to simplify things down. And sets and logic are all directly connected. They're both all in it. So you can do other sorts of things, which I'm skipping at the moment. So that's the end of the sets section, and so that covers the last few questions on the last week's drill, which I didn't otherwise. We didn't do otherwise do in class, just the proving stuff.